Okay, good morning, everyone. So today we invite Professor Sijie Luo from Central South University in our seminar to give a talk. And he will talk about no-commutative functional inequalities and their application. Let's welcome.
Many thanks to Professor Huang and Professor Wu for their hospitality, and I'm very happy to have such chance to give a talk here. And today I will focus on functional inequality, of course, but our second framework is non-commutative second. Okay, and my talk today will contain 3 sections. And first I will begin to give some background on the study on functional inequalities. And there's 2 very concrete models inspire us most is the Gaussian space and hypercube. And why we're interested in functional inequalities? Because they are essential tool in analysis, such as the study in multiple chains and PD and functional analysis. Okay, and I will begin with the following 2 types of functional inequalities, which is one of the most fundamental inequalities in the theory of functional inequality. The first one is named the Poincare inequality, and the second is named the log-Sobolev inequality. Okay, as a statement, what is the Poincare inequality? It means that if a function defined on the Gaussian space, if the gradient of f belongs to L2, then f belongs to L. Okay, this is Poincare inequality. If we state it as the inequality, it means that the energies domain the variance of f. Okay, this is the Poincare inequality. But in that settings, this inequality is not sharp enough because the log-Sobolev inequalities could give us more. What? Because if f, the gradient of f belongs to L2, then f is not only belong to L2, it belongs to L2 log L. It's the sigma space. Okay, you know what is L2 log L? It's some kind of origin space generated by convex functions like t power 2 and log t. Right? And the second word is named the log-Sobolev inequality. Okay. This is the 2 fundamental functional inequalities in Gaussian space. But Gaussian space is one of the important models that inspire us. But in today's talk, we will focus ourselves in another model named the hypercube. Why hypercube? The reason we're interested in hypercubes, we have the following 3 motivations. Because at first, when we focus on hypercube, all functional inequalities will have a simple form, right? We can see later. And also, if we get a result in hypercube, we can use the central theory to pass from hypercube to Gaussian space. So the hypercube functional inequality is material in general. Okay, and the last, the study of hypercube functional inequality of hypercubes is motivated by the study of Boolean analysis, which is the important part or important topic in computer science, right? That's the social voting rule as the study in Boolean function. So there's 3 motivations why we focus ourselves in hypercube. Okay. Then what's hypercube? Hypercube is so simple. It's a Cartesian product of Z2 next here. The -1 and 1 and the Cartesian product and dimension. Okay, and we equate this group with uniformly distribution. And in the hypercube, we can define the partial derivative as follows, because in this setting, this is totally discrete. So we could only define the partial derivative by the difference, right? And why is 1 over 2 here? Because in one position, if we flip this prediction from 1 to -2, 1 to -1 or -1 to 1, the distance is 2. So it's why we have a 1 over 2 here. And also this Cartesian product, the Z2 is the Arminian group compact, right? So we can use the character that's named the word system defined for this is WA, the word system, and A stands for the subset of from the set 1 to n. Okay, and this guy WA named the word system and form an orthogonal base in L2, the hypercube. Okay, and by this orthogonal base, we can define by the Fourier transform of the Laplacian operator, or here we name it of number operator. Okay, the number operator. 为什么这个后面是？Okay, and this guy is the number operator, or another name is the Laplacian operator. Then we can also use this n to generate a systemic group. Okay, and the relation between the Laplacian operator and the partial derivative will stay as follows. Okay, this is the spectrum. And now, by use the spatial gap inequality or the spectral theory of the Laplacian, this Poincare inequality is trivial, right? Because we only need to use the orthogonality to give a representation of n. Then we can see that when n is the number operator, then we'll have a spatial gap, right? It's 0 to 1. So it's easy to get the following Poincare inequalities. This one is trivial. It's only a consequence of the spatial theory. But the following result is non-trivial. As we know, almost all functional analysis and harmonic analysis is always do research from p equal to 2 and to general p. And this result, the result from Talagrand, it means that this Poincare inequality is not only hold in p equal to 2, it always hold in for p bigger than 1 and smaller than infinity. And the proof is non-trivial because they use some isoperimetric inequality and some decomposition of the hypercube to get such result from p to 2 to general p. This Talagrand result on LP Poincare inequalities. And also, if we only focus on the two L2 Poincare inequalities, there's more we can get. It's the foreign named the Talagrand's L1, L2 inference inequalities. Because in the Poincare inequalities, there's not the term here, right? But when p equal to 2, we can get the following result. It's certainly bigger than 1, so it's stronger than the Poincare inequality. And why you get such a result, it seems so strange, because this result can be used to deduce KKL inequalities. In next step, if let's say if f defined here the Fourier function, then the Poincare inequalities states that we only have these relations. Up to a universal constant. Right? This is the consequence of Poincare inequality. But the KKL inequalities that say that there's something more. We can have the result as follows. Also a universal constant, but here there is the log n. this is the consequence from the Talagrand. And also this one called the KKL-conjecture, right? So this one is important in Boolean analysis and well known and have many uses. Okay, and the next question is this one is the KKL-conjecture, and also in 1994, another result from Talagrand proved some kind of exoperimetric inequalities in his research in what is space area functions in Boolean cube. Then he leads him to conjecture there is the inequality that can unify his isoperimetric inequalities and the KKL inequality in an elegant way. And this result is resolved by Eldan-Gross in 2020. He proved the following result. He also restrained, but this result could combine the Talagrand's isoperimetric inequalities and the KKL inequalities in the one form of this way. So, and as we can see here, there is the L1 norm of the gradient f. So it's smaller than the L2 norm of gradient at first. So it's this one, and this one is all this term is always bigger than 1. So this result is always stronger than the L2 concurrent inequality. Okay, always the result can stay here is always stronger than the trivial concurrent inequalities in hypercube. Okay. Result. Okay, here is the story of concurrent inequalities on hypercube. Now we turn to the log-Sobolev inequalities. And the first log-Sobolev inequalities and its equivalence named the hypercontractivity is proved by the Bonami and Nielsen in 60s and 70s. It stated the semigroup generated by the Laplacian operator is not only contractive, it is hypercontractive with if the time t satisfies this relation. And this t is optimal because when t is smaller than this, and this operator is non-contraction. Okay, this time the time we say here is optimal. So this one is the optimal hyperconductivity, and Gross in 1975 proved that this result is equivalent to the following log-Sobolev inequalities, and he used the central limit theory to pass the result from hypercube to Gaussian. So in his proof. So this one is the log-Sobolev inequality in hypercube.
那个 n 是啥东西？
这个this is the number operator, and here. Yeah, or the Laplacian operator. Okay, this is the story of the log-Sobolev inequalities. Okay, and can we say something more about the log-Sobolev inequalities? Because the log-Sobolev inequality here, it means that the energy domain the entropy of F, right? Entropy of F is L2 log-Sobolev inequality. So it's quite natural to consider if we can get something about p-log-Sobolev. Okay, but from 2 to general p is also non-trivial here. And here at first we use the gradient operator. Here is the L2 norm of the gradient of F here. And it also results due to Talagrand. It proves that this one. It looks a little bit strange. It means that if f is a mean zero function and the gradient of f, the LP norm is strictly smaller than 1, then this one is bound. Okay, and this one is bound. And this one you can view it as a p-log-Sobolev inequality. Why? Because we can see the following. In the Talagrand result, we can state as follows. If the gradient of f belongs to LP, then f is belong to LP log L with power p over 2. And but when p becomes 2, and this result is reduced to the log-Sobolev inequality, right? Because p equal to 2, and the first one is L2 log L. Okay, but this result can extend to general p from 1 to infinity. Is a result. And also in 2009, two authors named Chi and Pick. They proved that the LP and LP log LP over 2 is the optimal pair for Gaussian-Sobolev event. What it means? It means that if we fix the domain here, and this one is the smallest space around the symmetry space. It's the you can view it as the stronger node around the space of symmetry space. So, and if we fix the target space LP log L and P over 2, then LP is the largest domain around the symmetry space for the Gaussian-Sobolev event. So this pair, they call it the optimal pair around symmetry space, around symmetric function space. So this pair is optimal. But this result has the first proof by the Talagrand in hypercube, and also can generate by generalized to Gaussian space. Okay. Now, this is about some historical background on Poincare inequalities and logical inequalities. Not only for general P and P equal to 2. Okay. Now we will turn to the following topics on non-commutative functional inequalities. Okay. Okay. At first, when our first investigation to do the research in this framework, we must ask ourselves, why we care about non-commutative? Okay, because at first, after our investigation, we know there's a conjecture in quantum information theory named the quantum KKL-conjecture. It means that if we extend such result from hypercube to the quantum setting or quantum Fourier cube, the KKL inequalities is unknown. It's a conjecture known in the quantum information theory. And second, you know, there's a group in Central South University. There are a lot of people focused on the non-commutative martingale inequality and non-commutative harmonic analysis. So the study of functional inequalities is also related to that topics. And also, the study of functional inequalities is also can be used in the study of quantum multiple semigroups. Okay, but this is don't talk such application today, but I will outline some conjecture that is interesting. Okay. At first, what is the non-commutative hypercube? And my first time of learning, I learned that there's someone named the canonical anti-commuting relation algebra, and we can call it the CAR algebra. Is one of the concrete model for non-commutative hypercube. Okay, and its definition is quite simple. It can be realized by the tensor Pauli matrix. Okay, this is the Pauli matrix, this UPQ, this guy. And if we for every j belong to n1 to n and qj's, the first j minus 1 term is u, and the j term is q, and the last n minus j term is identity. So this one qj, you can view it as a non-commutative Radamas random variable, right? The non-commutative Radamas random variable. Then qj is set at Zhou and is the unitary and satisfies the following CR. Means this one. And this one is the non-commutative random variable. The non-commutative Radamas random variable. Then we can use it to generate word system, which can define as follows. For every A, we can order A in the increasing order. Then QA means the product of QI1 to QI, the cardinality of A. And this QA get together, we can get the orthogonal base of L2 of the CR. And if also from the orthogonal base, then we can use the Fourier expansion and define the number operator and partial derivative. Okay, And for every t, it has this following representation. Okay, and this one stands for the Fourier coefficient. The Fourier coefficient. Okay. Now we can similarly to define the partial derivative as Fourier bottom right. Right? Is we choose the prediction that y when A contains J, this coordinate. And when we sum this dj together, we can get a so-called number operator, and y the minus one, the minus number operator will be called the operation operator. Then when we get the operation operator, we can get a semigroup. Then we can do some research. So about use the spectral theory to get the Poincare properties. Also, we can mention here. To get the L2 Poincare property here in the CR algebra is trivial. It's also a consequence from the spectral theory, because there's also a spectral gap here. So to get such a result is not difficult, it's trivial. But if we get the result from 2 to general P, and this result is non-trivial. This result first proved by Louis Pica and co-author, and which there's followed, and his proof is not rely on the same group. His proof and their proof rely on the one parameters group S. This is some kind of very likely to the rotation invariant of Gaussian measure, something like this. So you can use the one parameter group's mass to prove the following LP Poincare properties. And also there's the gradient here is looks a bit little bit strange. But when t becomes to hypercube, and when t becomes to when the m here becomes to hypercube and t becomes to a function, define the hypercube with value in R, and there's everything is set at the join. So the star here is disappear. Only this term, and this term is R when m become to hypercube, this one become to Rj. Rj is take value only 1 or -1. So absolutely value of this term equal to dj itself. So we reduce to the classical LP Poincare properties.
它这个梯度是怎么定义出来的？还是说在证明的时候它就是自然这样出现？
它是用了一个非交换平行不等式。因为非交换平行不等式，它有一个取 maximum， 以及在 LP P 小2的时候是做一个 partition， 但无论怎么样，它就做到任意 P 嘛，所以它就往大的方向放，就放成大的。它其实是小的时候呢，是它的分解去 infinite， 大的时候就是这个东西，所以它就往大的放，就其实用了平行不等式做的。
它这个算子定义有没有什么要求啊？就是说只要是合理的都可以是吧？
哪个算子？
梯度就是 lambda s。
对，就是第一点，你必须能回复回去，并且它就是某种偏导数的 L2和嘛，你必须有这种结构出来，它都可以。
都可以。
对，乃至后面有关于那个 Buckley 他们那种伽马伽马算子也可以，就是这种东西，只要你能满足这些类型的这种东西都可行。Okay. As mentioned here, this gradient term is strange, but it is a consequence from the non-commutative thinking inequalities from Louis Pica and Lee. Okay, so it looks a little bit strange, but it coincides with the classical case. Okay, this is the story of the non-commutative Poincare properties on CR algebra. And also, we were interested in the long inequality, and this result is earlier than the Poincare properties. It has been proved by Carl and Lieb in 1993. Okay, it proved that all these inequalities are the same with the classical inequality on hypercube and Gaussian space. It's the same, but the proof is different because in this proof they rely on a very fundamental result of case law, Carl and Lieb in 1992. They proved that for non-commutative or the short-term P space, they compute the optimal constant of the short-term P space for their uniformly convex constant. Something like this rely on some very technical commutation. When we get the commutation with the get the optimal constant there, then we can prove the result for the optimal hyperconductivity and use the optimal hyperconductivity to derive loss of inequalities. The L2 loss of inequality. This is currently left to result. Okay. Okay. And here is the story on functional inequalities of the non-commutative setting, but something I should mention here. I think it's very interesting because you know, when I was a postdoc here, I worked on the concentration inequalities for Banach space valued real variable. And there's a very breakthrough made by Ivan Handel and Bomberg. They proved that for a Banach space with non-trivial cotype, okay, I don't give the precise definition of non-trivial cotype here, but you can think as a very weak condition imposed on the Banach space. Okay, because when a Banach space with non-trivial cotype, then the following vector value Poincare inequality holds. Okay, the vector value, and this term, you can view it as a vector value gradient term. Why? Because when x or b here become to r or c, we can use kinking inequality here to get the gradient of f and LP naught, right? Because when b becomes r, we can use kinking inequality. But when B is general Banach space with non-trivial cotype, the only right way to state the Poincare inequality is as follows. It's a very important result by Ivan Handel and Bomberg. Okay, why this result is important? Because they solve a long-standing open problem in Banach space, whether the envelope type and the Rodman type coincide with each other. They use the vector value Poincare inequality to prove the following. Okay. At first, I will mention what is Rodman type and envelope type. Rodman type is vector value kinking inequalities one side kinking inequality for vector value real variable. And what is envelope type? By Bayesian reformulation, envelope type is something like Poincare inequality. Okay, but the Poincare inequality implies the kinking inequality is trivial, but by choosing a specific f, the sum of the Rodman series, that is the sum of Rodman's real variable. But the converse direction, if the Rodman type implies the envelope type, it's a long-standing open problem, and it's finally solved by these three authors in 2020. They proved that this one is the envelope type constant. It controls the Rodman type constant here. But this term is also controlled by the Rodman constant with up to this universal constant. Okay, this is a consequence from the result I presented before. This consequence is a consequence from this result. So it means that for the general Banach space, the envelope type and the Rodman type coincide with each other. So it's very important. And after that result, there's a lot of generalizations from vector value Poincare to vector value Talagrand and vector value log-spread inequality, and they define a lot of metric type and investigate their relation to the geometry of Banach space. So there's a very interesting topic here. Now, this topic is focused on the Banach space theory, so it's not the main topic today, but I should mention here, it's interesting. Now, I will finally talk about what we're doing. Okay? What we're doing. Okay. Our motivation is quite easy and natural. Okay? As we can see here, from P equal to 2 to general P, right? From Poincare inequality LP for L2 Poincare inequalities, we would like to investigate whether there is LP Poincare inequality. Okay, but this result has been proved. The LP Poincare inequality has been proved by Luis Pita. So it's quite natural to consider why this only for the L2 case. It can be strengthened to Talagrand's L1, L2. Why not L1 LP? It's quite natural. right? So we like at first, if the LP Poincare inequality can be refined into L1 LP time, Talagrand inequality is our first motivation. And second, even for the L2 Poincare inequality, can we get something like the Eldan-Gross inequalities and use it to investigate the KKL-conjecture is our motivation. For L2, we'd like to get the Eldan-Gross inequality to investigate something like the conjecture. And also, as we all know, there's the logs inequalities only deal with the L2 logs inequalities. There is no LP of p-log inequalities before. So we were very interested in whether in what framework and whether we can get p-log inequality. These three our motivations. That's what we'll talk today. Okay. But the first one is easy because when p is strictly bigger than 1, we can get a constant here, kp, depend only on p, to get such result as Talagrand type of L1 LP inequalities.
这我有点忘记了，那个 MN 是什么东西啊？是那个 CR 的那个
Yeah 对，
是有限的，是无限的，为什么？
有限，
哦，
都做有限，目前都做有限。对，因为无穷的时候在求和你确认收敛性就麻烦一点，那现在都做有限。
所以这个是不一定趋于无穷的时候不一定这个极限存在，是吧？
趋于无穷的时候，你要先描述这些极限里面都存在，但这个常数不依赖 n， 这个 k 是不依赖 n 的。
对啊，那也就是说是可以趋向于无穷，对吧？
对，就形式上可以趋向无穷，但我们要去讨论说你在趋向提穷的这种拓扑上，到底是不是真的可以过去？对，我在 fix n。Okay, kp here is the kp is depend only on p, is independent of n here. And here we use another notation here is L2CR. Okay, you can see this term is come from the non-commutative pinching inequalities. It means that when p is strictly when p is bigger or equal to 2, and this term is something like the Picas gradient term. When p is smaller than 2, this term is much more smaller than Picas gradient term. When p is smaller than 2. Okay. Then we can get the results from L1 to LP Talagrand inequalities. But this result is only refined of LP inequalities, but could not use to investigate the KK inequalities. So this one I will don't talk too much here, because this one is only refined the Poincare, but we don't for any application with this guy. Okay. And second, unfortunately, we get a result of the Eldan-Gross, but our proof relies on the semigroup and something like the random restriction to get a result very similar to the classical Eldan-Gross equality. Because the Eldan-Gross equality is the formula for a function that named the Boolean function, right? Boolean function is the function defined on the hypercube with value only 0 or 1. How to reformulate this guy into the non-commutative setting is a very simple candidate. It's a projection, right? This one is projection. So we should prove such result for every projection in the CRI, right? So we get the Eldan-Gross equality. Now, when we get the Eldan-Gross equalities, we are interested whether such result can be used to investigate the KKL-conjecture. Okay, now we will return what is KKL-conjecture. It posed by Montanaro and Osborne in 2010. Okay, but their framework is something called the quantum Boolean cube. Is something different to the CI, but they're similar. I will talk about this better later. What they conject? They conject there is a universal constant here, such that for every balanced quantum Boolean function, what is balanced quantum Boolean function is satisfied the following step. The operator is unitary and the balance with 1/2. Then I conject that if the inverse, okay, this term is this term, is bigger log n over n is the projection. Because in their proof, they could not get such result. They could not get such result. And the inference is the inference of Q in L do not or 2. Okay. And what is the quantum Boolean Q? Okay, I will put the diagram here very quickly. It's very similar to the CAR answer. It's also defined by the Pauli matrix. Okay, this one, but we denote by sigma 0, sigma 1, sigma 2, sigma 3. Okay, and sigma s you can view as the Y system. It's the tensor. We choose this guy because S is a vector and every projection is from 0 to 3. Okay, then we can choose every sigma here to their different projection, and this sigma s on a orthogonal base, and this one will become a orthogonal base of L2 of the matrix, and every element here can represent as this form, and this guy is also a Fourier conjecture. Okay, and this is the framework for quantum Fourier cube. It's quite similar, but in the CR algebra setting, we only for every Q, but because what is the Rademan sequence here? Because it's sigma s, and the s with only one projection is non-zero, right? Only one projection is non-zero, it will be the non-commutative Rademan written variable here. But in the CR algebra settings, there's 4j minus 1 term is U and the j term is Q. It's quite different. So in this setting, there's a lot of commutative ring variable here. And okay, this is the part the partial derivative defined by Fourier multiplier. And also we can use the Laplacian of number operator here. Now what is S? S is the cardinality of the spot of S. And spot of S is the projection of non-zero projection. Non-zero projection. So we can see here the counting of the cardinality here is quite different to the CAI. Although the construction is similar, but the counting of numbers of the cardinality here is different, so it can affect the behavior of the semigroup and finally affect their different phenomena of the functional equality. We can see this later. Okay. And this is a very recent result by Bomberger and this three guy. Then prove that in the quantum Fourier setting, there is a constant, universal constant K here, such that for every P is bigger or equal to 1 and strictly smaller than 2, then such KKL inequality holds. Okay, and in their proof, they are interested in when P equal to 1. They call it geometry inference because the geometry inference is has already been studied in Gaussian space. Okay, so and we can see such constant here. Such constant will prevent them to get the result when P becomes to 2. Okay, when P becomes to 2, D1 is 0. So the inequality is treated. Okay, but when P is strictly then 2, the result is fine. Okay. Okay, and that proof is also relies some kind of variant of the Talagrand inequalities. Okay, this is their result.
但是一般这种可以取一个导数，
哪个？
就在 p 等于2时候取一个导数，有没有可能？
就倒过来是吧？
我就是求导趋于0嘛，你某种意义上就是应该有这种求导的方式。
嗯哼，
可以得到一个另外一种可能性，我不知道。
我知道， 在 T 点处发现它是求
对，
导。
因为你这个地方有连续的这个信息在，那是非平凡的，不可能说是把一个 p 等于2带进去。
对，对，在这里刚好在这个点处求导。对，因为你在这边左边去求，你发现 P 开完之后，你左边去求，可能会求出一个类似商的东西出来。
对，不可能有些信息是丢掉的，我的意思是会，
对，
也没有什么其他意思。
OK，
对，我猜测有个更简单的，
有更简单。
更简单，不的。
嗯，
对，这样的话你可以在 p 等于2的地方求导，
对
因为如果这边不能求导的话，说明这不是很简单。
对，
还
就是很差，这还差
缺一点东西。
还差一点东西。对对对，好，OK，I will continue. Okay, but as I present for, okay, but the Eldan-Gross equality we get is in the framework of CAI algebra. It's not a quantum Fourier truth, although they are very similar. So we are interested whether if we ask the result for the CAI algebra, whether the KKL-conjecture hold or fail. Okay, but it's quite interesting. In the CAI algebra, this conjecture is fair. It's very easy to construct such example. Okay, we can see here because T is the distance is the 1 over square root of n and the sum of the non-commutative Radman ring variable. Then you use the anti-community relation to compute that T is set as mean zero and neutral. Okay, so it's a quantum Boolean function, but djt is this term, so it means that for every p, this term is 1 over square root of n. So this one is become 1 over n. So it means that the Poincare inequality is already solved in this way. Okay, we could not improve in the CAI algebra, but the quantum Boolean cube stacking is unknown, but the CR is quite easy to answer that this result fair in this stacking. But what we can say from Eldan-Gross, okay? At first, we get the result by using the Eldan-Gross. It means that there is also a universal constant here. And for every epsilon belong to 0 to 1, you can treat as a very small universal constant. Then one of the following statements hold. The first one is the KKL equal, or the geometric inference will much more stronger than the n log n1 over n, because this one is quite close to the square root of n. Okay, that means that in one case the KKL-conjecture hold in the CR algebra, and otherwise there is the improvement of the geometrical inference here. Okay, we get this phenomenon because at first you can see here for our total example. For the L2 case, this one becomes to 1 over n is short. But if when we turn to p equal to 1, this one is the square root of n, right? So this one holds. If this one is failed, then this one holds. So we can use it to deduce the result from the Eldan-Gross equality. This is our first application of the Eldan-Gross. And second application, we'd like to measure how non-commutative of a Boolean quantum Boolean function. Then use something like index to alpha here to compare the L2 inference and the geometric inference to alpha here. Then we can prove that for every balanced projection from the CR algebra, the index is always belong to 1 to 2. But for every n and every Boolean, every balanced projection, if the index is strictly smaller than 2, then the KKL conjecture holds. Here, if the index here is strictly smaller than 2, then we can get such a result. Okay, up to a constant c depend only the index of p. But when we reduce to the classical setting, when the CAI algebra becomes hypercube, and every Boolean function will always have the index 1. So this one will become to the universal constant. So we can reduce to the classical KKL inequality. But in the non-commutative setting, we would like to get a result depend on the index. Because when the index is become to 2, that's called the example there. But when p is stricter than 2, then we can get such result. This is one of the KKL-conjecture in the CI algebra. But in the quantum Fourier setting, we don't know. Because we don't have any code example. Okay. So this is the story about the refinement of functional inequalities for functional inequalities on CI algebra. OK，
所以 balanced projection 就跟 projection 不是一回事吧？
就是它要求它的 variance 等于1/4，所以就是在经典的时候，它是有一半取1，一半取-1，大概是这样的。其实做一个 scaling，就这种很高的。
OK， 但是如果说这个 projection 换成别的算子，这个可能就
它其实就在
不一定成立
前面这个地方多了个 variance，就
嗯
多了个 variance p。那经典就是多了个 variance p，对，就不是 universal constant。
OK，
Okay, this is the story about the functional inequalities and their application. Now we will turn to the loss inequality, which are also interesting. Okay. Now, but when I have talked about the functional inequalities, we focus on very complex models named the CAR algebra. But when we turn to the loss inequalities, we focus on the abstract setting because at first we also like to do something in the complex model, but after we finish our proof or complete our proof, we find such result don't rely on any technique from the complex model, so we stay in the abstract form. Okay. Now M here is the trivial von Neumann algebra, and P is bigger than 1 and strictly smaller than 0. And alpha is a real number, and this one is called sigma space, and we will use a shorthand notation by here. Okay, it's a sigma space. It's R space generated by a function like this, t power p and log t with power alpha. And also, there's a gradient term named Meyer gradient form. It's taken from a book from Barclay Ledoux in 2014. It's gamma. You can view it as a gradient term here. It's quite abstract. And also, okay, this one is called gradient. Now, what is the p-log inequality? What is the setting? Our result here is abstract. What's abstract? It means that for every hypercontractive semigroup acting on a tracial von Neumann algebra, and if the Ritz transform here is bounded, we only impose these two conditions. One is hypercontractivity, and the second is boundedness of the Ritz transform. Then we can get the result for journal p-log inequalities. Because this one means that if the gradient of f, the gradient of x belong to LP, then f belong to the sigma space LP log L and with power p over 2. Okay, this is the result. Then we only use is the hypercontractivity. The hypercontractivity is necessary because when p becomes to 2, this result will reduce to the classical L2 log inequality. So the hypercontractivity is necessary. Okay, but we also need the use of the Ritz transform. Okay, but we do not know whether the hypercontractivity has already implied the boundedness of Ritz transform. We don't know, so we use it as a condition. But everything we use is only the hypercontractivity. Okay, I will outline some difficulty in our proof because at first in Talagrand, the proof of p-log inequality, one of the most important tools he used is the isoproximation inequality. Is to measure the sphere and the volume of some major set. Okay, but some kind of isoproximation inequality, I think that it could not be derived from the hypercontractivity or Ritz transform. Okay, it's not a consequence of our assumption. So the approach is failed in this. And second approach of the p-log-Sobolev by Buckley and May, and also Fisherman, then also use the Brownian, and they prove the p-log-Sobolev in Gaussian space. And the fundamental tool they use is the following. The first is the Brownian motion, and second is the little Paris dance theory, and some rich potential theory. And all such results, just like Brownian motion and little Paris theory, is not well established in the framework. Only we impose that it's a semigroup which is hypercontractive. Okay, that result is also invaluable in our setting. Okay, and third, there is in the proof of Qian Peak in 2009, they proved the optimal Sobolev embedding theory. They also proved the result in the Gaussian space, and they also used the isochromatic inequalities and co-area formula. And also such result, co-area formula and isochromatic inequality we could not relate it to the hyperconductivity and the race transform. The problem is the race transform. So we like to use some different idea to different approach to get the result. And how to prove this? The main tool we use is the same interpolation. Of course, the same interpolation is necessary in our proof, but we prove the following abstract result at first. If we prove what? We prove if a T is a positive operator and satisfies these three conditions, then if the abstract operator here, we have these three conditions, then we can get the following estimate. Then if Tz is bounded from this Ligman space to this Ligman space, and here Z is the real part of Z, and P over 2 here, P over 2 is important, P over 2 here. Okay, we prove this result. And why we prove this result? Okay, it's here a little bit strange. We see this result first. Because that T is P plus 1. What is P? P is the generator of this hypercontractive semigroup acting on the tracial non-algebra. Okay, this P, when P plus 1, okay, I think that is P minus 1 and 1 over 2 here is the guy that we use T. That T, we prove the result of T, and specifically we will replace T to P minus P plus 1, and with this part this one is the basal potential. Okay, then we prove that for every hypercontractive semigroup, the basal potential satisfy these three conditions. The first one is the decay from L infinity to L infinity with this term. And second is the LP to LP boundedness with the imaginary power. And second, and the third result is this basal potential is bounded from L2 to L2 log L. This one is very similar. It's quite close related to the loss of inequalities. Okay, this is our result. First, for hypercontractive semigroup. Then our result, if an operator satisfies this condition, then can get the result is not only for 2 from L2 to L2 log L. It will always from LP to LP log L of some power log L, right? The general P when P strictly bigger than 1. Okay, the first. But unfortunately, this result we finally prove is for the risk potential. But if we would like to use the boundedness of risk transform, we would like to know the boundedness of this one. We exactly would like to know the boundedness LP boundedness, this one, but not this one. This one is the basal potential, and this one is you can see as risk potential. The final thing we'd like to know this one, but not this one. But we prove the result for this guy. So finally, we are conjecture that whether the hypercontractive have already implied the equivalence of these two guys. Okay, in some complex setting, just like Gaussian, of course, they equivalent to each other because they can use some kernel estimate, the pointwise kernel estimate. But for pointwise kernel estimate, it's invalid for our setting. So we studied such binomials for weeks. Then finally we emailed to Bonami. Bonami is the first one to establish the hyperconductivity. We asked her whether the hyperconductivity already implied such equivalence in actual setting, not complex setting. And very quickly she replied to us. So stated she don't know, but you can try some idea from the spectral theory. She don't know, but you can try by some spectral theory. But finally, we use some spectral gap and some decay of the semigroup finally to prove this result. Okay, this result looked a little bit strange. Okay, it's the boundaries of this guy. Boundaries of this guy. Okay, why this guy? We can see here. Okay, why this guy? I can write here because we get the result of the boundaries of this one. Is this one b minus 1 and here is 50 LP. Something like this. This one is what we have yet, but the result I would like to transfer this guy to this guy, right? Now I can use this one because at first when we have this one minus z, yeah, what's this one? This one is spectral theory. Okay. This one is okay. This term is we have already controlled, but we remind this term. And what is this term? This term is 1. Right? But if we have the boundary distance is this guy, then we can use the boundary distance. So P1 minus this one. The P and this one we have already proved this one is boundary. So P2. So this result we use is to transfer from basal potential to risk potential. This is why we prove such look a little bit strange result because this result is only a consequence from hypercontractive. We don't use any pointwise estimate and some kernel predictions because in this setting there's no kernel. Okay. That's the result. Okay. Now finally we prove this one. It's the so-called functional boundary many estimate. It means that the risk potential, if this one is the hypercontractive semigroup, then the risk potential is bounded from this sigma space to this sigma space. And when we choose J is 1/2 and use the boundaries of risk transform, we can recover the p-log-Sobolev. Okay. And this is the p-log-Sobolev. Okay. The p-log inequality. But one thing I should mention here, p is strictly bigger than 1. We could not deal with the case when p equal to 1. Okay, this is the main problem we'll consider most is here. Okay, also as the corollary of the p-log inequalities, we can also get the Talagrand isotropy matching inequalities. It's also stronger than the Poincare inequality. Okay, this guy is the gradient guy, corresponding to the p-cast gradient guy, but this one is strictly bigger than 1 regarding this one. Okay, we have this term, so it's bigger. This one is bigger, so this result we can use this result to deduce p-cast Poincare inequality. But the Poincare inequalities have a Q, but in this result we can also hold in every every setting of hypercontractive semigroup with the boundaries of the reciprocal the Richard form. Okay, this is the some kind of isotropy matching inequalities, and we find the Poincare inequality. Okay, finally, I should mention some open problems that we consider most recently. The first, no doubt, is the quantum KKL-conjecture. Okay, whether for quantum Fourier cube, the conjecture is whole or fail. Is true or fail? We don't know. But regarding our investigation in CR algebra, maybe it failed, but we could not construct such counterexample. But maybe it could hold because in the quantum Fourier setting, there's a lot of commutative random variable there. It's much more commutative. So its phenomenon will be a little bit like commutative, not just anti-community. This is our first problem. And the second problem is whether our assumption of hypercontractivity semigroup has already implied the boundaries of Richard form. We don't know in the actual setting, because in the complex setting, the boundaries of Richard form can be deduced from some kind of curvature condition. But curvature condition is also stronger than the hypercontractivity in many settings. So we don't know the hypercontractive has already implied the boundaries of Richard form or not. We don't know. And also in our proof, we could not deal with the case when p becomes 1. Because the first thing is the hypercontractivity assumption, the p and q here is strictly bigger than 1. We could not, so it means that we could not impose any condition when p becomes 1 is the first. Because the hypercontractivity, we have no information for p becomes 1. And second, the boundaries of Richard form for p becomes 1 is fair, because in the Richard form, it's not bound for p equal to 1. It's bound from L1 to weak L1. Not L1. It's from weak 1, L1 to weak L1. So we like to know, we need what kind of conditions on the semigroup could ensure us to get p-log inequalities to take over the case when p becomes 1. And this is the 3 open questions that we consider most. Okay, and now thank you very much.
Many thanks to Professor Sijie Luo's wonderful talk. Any questions?
So I have one. So you said that the quantum KKL conjecture fills in the CAR